In the last class we defined resolution of identity. I will repeat it quickly before we go ahead, and we proved some results about projections which we will be using today. So, using the resolution of identity, we are going to define an integral with respect to resolution of identity. So, I motivated it by saying that resolution of identity is like the cumulative distribution function of a probability measure, and one can define what is known as the Riemann-Stieltjes integral with respect to an increasing function, right. So, with appropriate conditions on the function. That is precisely what we will be doing, except that the resolution of identity takes values in the space of projections, and so when I develop integration, it is going to take values in the space of bounded operators on a Hilbert space, right. So, this is like integrating against the projection valued measure. So, I will demonstrate that these are equivalent in an example which is very easy to see. We will not get into the details of how to get a projection valued measure from a resolution of identity, okay. But at least we will see it in a easy example that they are sort of same, okay. So, let us start. So, recall the resolution of identity. Resolution of identity. So, we denoted it by E sub t, right. So, we had t going to E sub t, t belonged to the real line, E sub t were projections, right, and it had three properties: monotonicity. So, one was t less than s implied E t is less than or equal to E s. So, these were orthogonal projections. So, self-adjoint ones. So, E t less than or equal to E s meant E s minus E t is a positive operator. 2 at minus infinity t going to minus infinity E t was the 0 operator, and as t going to infinity E sub t was the identity operator, and 3 was right continuity with respect to right continuous with respect to the strong operator topology, right. So, we had defined all this earlier. So, let me not spend too much time on that. Let us give an example which will make this a bit more clear. So, we can look at the Hilbert space H to be L2 of the real line. Okay. Now, I want to define a resolution of identity. So, that is t going to E sub t. E sub t's are all projections. Okay. So, define. So, I should tell you what E sub t is, right. So, E sub t is going to be an operator from H to H, which is an orthogonal projection, right. So, E sub t of a function f is in L2 of R is simply multiplication by indicator of let us say t times f, right. So, it is multiplication by the characteristic function of the set minus infinity to t, and it is easy to check that this has all those properties. For example, the first one, if t is less than or equal to s, that monotonicity property, right. So, if t is less than s, then well, what happens if t is less than s? You have t here and you have s here, and you are looking at some interval like this and another interval like this, right. So, these are the two intervals you will be looking at, and you are multiplying with the indicator function of that. Essentially, you are restricting the functions in L2 of R to the interval minus infinity to t, right. That is your projection. Okay. So, well, it is a projection because you are multiplying by an indicator function, and if you have seen that this is an orthogonal projection, right. So, if t is less than s, then well, what happens to E t? So, E t, so I want to say E t is less than or equal to E s, right. So, that is the thing we need to check, but that is same as E t. So, I look at its action on some function and take inner product with the same function. So, I need to look at E t f inner product with f, right, and see if it is less than or equal to E s acting on the vector inner product with the same vector, right. This is what you mean by E t is less than or equal to E s, right, or E s minus E t is a positive operator. Well, this is trivial because this is nothing but, so what is the left hand side? This is nothing but integral. Well, E t is multiplication by the indicator function of minus infinity to t. So, this is minus infinity to t f bar, right. So, let us write f of x f bar x with respect to the Lebesgue measure, right, because I am looking at L 2 of r, right. So, this is simply minus infinity to t mod f of x square dx, and then you know, now you know what to do because t is less than s. So, this is of course going to be less than or equal to integral minus infinity to s mod f of x square dx, right, because I am integrating a positive function, right, mod f of x square. So, if I integrate over a larger set, I am going to get a bigger value, which is simply because of whatever computation we have just done. This is ESF inner product with f, right. So, we will see that the monotonicity is true, and I will leave the remaining to you that when t goes to minus infinity, of course, it will go to 0 because I am looking at minus infinity to t norm of f. Okay, so, maybe we can do that as well. So, at least one of them, because the other one is exactly the same way. So, if t goes to minus infinity, what happens to ETF? Okay. So, what is ETF? ETF is going to be indicator of minus infinity to t times f, right. The L 2 norm of this, right, the Hilbert space norm. So, this is L 2 norm of equal to minus infinity to t mod f square dx, right, and as t goes to minus infinity, this will go to 0, right, by dct. Okay. So, which is same as saying that Et, that is, so that is E sub t f goes to 0 in the strong operator topology, right. So, E sub t goes to 0 in the strong operator topology, right, as t goes to minus infinity. Okay. And so, you check all the other properties as t goes to plus infinity, you know that it is going to become multiplication by indicator of the real line, which is 1. So, you have the constant function multiplying by constant function 1, which is the identity operator and things like that, okay, right, continuity and so on, everything you can check easily. Okay, but this is something which is supported on the whole real line. I can restrict this everything to, so let us look at one more example to see that how to construct some resolution of identity which is supported on a smaller set, right. So, take L 2 of some interval a b as your Hilbert space now, okay. And E t you can define exactly like the way you have defined earlier, except that now your domain is a b, right. So, you start from a, right. So, so E t is defined to be, so E t is going to be an operator from projection from H to H, right. So, E t of f is equal to, well, I should strictly speaking take a to t times f, okay. But this will make sense only if t is greater than a and less than b, right. So, one should say t greater than a, okay, greater than or equal to a if you like, and well, once it crosses b, it is indicator of a b, which is 1, and then that will be the constant function 1 as far as our Hilbert space is concerned. So, it is identity for t greater than or equal to b and 0 for t less than a, right. So, that is how it will be defined, and so this will obviously satisfy all those properties we want, and moreover by from our definition, it is clear that support of E t is contained in the interval a b, right. Here E sub t is supported in the interval a b, okay, right, that is clear. For any a minus epsilon, because of this the projection is 0, for any b plus epsilon, because of this the projection is identity, right. That is precisely what you mean by it is supported in the interval a b. Now, let us go back to let us look at this example or the first example, and see how we get a projection valued measure from here. Okay. So, let us see that. Okay. So, first example again. So, in the first example the Hilbert space was L2 of the real line, okay, and E t was multiplication by and E t was indicator of minus infinity to t times f. Okay. So, well, how do I get? So, if we recall, whenever we had a cumulative distribution function, how did we get the probability measure? Well, it was by essentially if you know Riemann-Stieltjes integral, one looks at the Riemann-Stieltjes integral with respect to f. Okay. But the way of defining this using sets would be, you look at sets of this kind, and this is simply f b minus f a. Okay. Then one can prove that it is a countably additive measure on the finite disjoint union of sets of this form, which is open at A and closed. So, half semi closed intervals, right, or semi open intervals, and then you can extend it, okay, to the sigma algebra generated by them, that is the Borel sigma algebra. So, if I want to do the same thing here, if I subtract E t and E s. So, let us take t s greater than t and look at E s minus E t. We will be looking at these kind of quantities later also in the abstract setting. So, this example will actually help you in understanding what is going on. So, E s minus E t acting on f. Well, what is that? That is indicator of minus infinity to s times f minus indicator of minus infinity to t in times f, right. So, the f is common, what remains is the difference between the indicator function of two sets, but one set is contained in the other, right. So, whatever is remaining, so that is the interval s to t, right. So, this is indicator of s to t, right. This is how f looks like, right. So, in our definition the measure mu is f b minus f a. Here once I have a measure, it should be a projection valued measure, right. So, the projection valued measure is on the set S t is multiplication by indicator of S t, right. So, the projection, so if I use P for a projection valued measure, I am looking at the Borel sigma algebra of the real line, and I am trying to define a projection valued measure there, taking values in L2 of R, right, projections on L2 of R. So, the start with, so in the definition of the measure, we start with intervals of that kind, right. So, intervals of this kind is multiplication by indicator of that set, right. So, let us be clear. So, we have seen that multiplication by indicator of functions are projections, right. So, these are your projections, okay. And then it is clear that the projections for well, this is not fully justified right now, projection for a set E, well, E I have already used. So, let us use F. If I take a Borel set F, the projection F corresponding to the projection corresponding to f is going to be multiplication by indicator of f, right. So, this is what we have seen earlier, that these are projections, and that is an example of a projection valued measure, right. So, the resolution of identity we have defined here is associated with the projection valued measure here, and you can also go back, right. If you have the probability, if you have the measure here. So, let us look at this. If I have the measure, how is f defined? So, f of any point t is simply the measure of minus infinity to t, right. So, the E sub t, which is the resolution of identity, is measure of minus infinity to t, right, under the projection valued measure p, which is multiplication by indicator of minus infinity to t, which is precisely what our definition is, right. So, these are sort of you can go from resolution of identity to a projection valued measure, and the other way with some work. So, I am not saying this is all easy, but it is very similar to what you do in measure theory. So, keep that in mind, so that when we write down integration with respect to the projection, the resolution of identity, identity, that is actually the integration with respect to the corresponding projection valued measure which you have already seen. Okay. So, there will be some repetition or familiarity with these things. Okay. So, let us continue. So, let us write down the main result using projection the resolution of identity. So, call this proposition, let E sub t be a resolution of identity, let us say supported in minus r to r. Okay. So, before minus r it is 0, outside after r, that means anything greater than r will give me the identity operator, right. If I take a continuous function on this set, think of minus r to r as the spectrum of an operator. Okay. So, on the spectrum we have this projection valued measure, and then once we have the projection valued measure we have the resolution of identity, right. Like what we saw earlier, we are sort of doing the other way, we are starting with the resolution of identity and then trying to define operators using that. Okay. So, the spectral theorem will be written in terms of the resolution of identity, that is what we are going to do for self adjoint operators, because spectrum is contained in the real line, right. So, the proof of whatever the proposition, I will write down the statement fully, is like proving the Riemann integral, existence of the Riemann integral for a continuous function on a compact interval, that is what is going to happen. So, take a continuous function in minus r to r, let phi n g. Okay. So, I am going to define an operator for each n, I am going to define an operator phi n g. So, I am starting with the resolution of identity, right. So, each E t is a projection on some Hilbert space H, right. So, let us note that, because I will keep writing. So, E t are projections on a fixed Hilbert space H, right. So, that is the standard notation we will keep using. Okay. So, phi n g, I am going to sum up something. So, this is like the Riemann sum, right. If I have a continuous function on minus r to r, what do? I decompose the interval into smaller intervals, right, subdivide the interval into smaller intervals and choose points from that and then evaluate the function and then multiply it with the length of the interval and sum up, that is the Riemann sum, right. So, here we will do it in a systematic way, decompose the interval into intervals of length 1 by 2 n. So, minus r to r will be divided into smaller intervals of length 1 by 2 n sorry 1 by 2 to the n. So, the n stands for that. Okay. So, let me write down the expression and then it will be clear. So, it is a sum j equal to minus 2 to the n r to 2 to the n times r, okay, g of j by 2 to the n. So, if you look at g of j by 2 to the n, j goes from minus 2 to the n r to 2 to the n r, right. So, if I divide by 2 to the n, j by 2 to the n will go from minus r to r, and that is where g is defined, right. So, g of j by 2 to the n is well defined, and E. So, E is your resolution of identity, j by 2 to the n minus E j minus 1 by 2 to the n. Okay. So, what is this? So, let us look at this more carefully. If I decompose the interval minus r to r, so let us say there is 0 here, into intervals of length 1 by 2 to the n. So, there are 2 to the n intervals. So, if I have j by 2 to the n here, I have j plus 1 by 2 to the n here and so on, right. So, this length is 1 by 2 to the n, right. So, I am decomposing minus r to r into lengths of interval 2 to the n, right. So, each endpoint would be like j n j minus 1, and I am looking at the value at the right end minus the value at the left end of the resolution of identity, right. This is what you will do in a Riemann sum, right. If I had a So, forget the j by 2 to the n. So, if there is no E, it is simply j by 2 to the n minus j minus 1 by 2 to the n, that is the length of the interval, multiplied by g evaluated at one point in the interval, right, which is j by 2 to the n, and that is precisely the Riemann sum for g, right. Except that now instead of length of the interval, well, if you were looking at the Riemann-Stieltjes integral with respect to, let us say, cumulative distribution capital F, you will have f of j by 2 to the n minus f of j minus 1 by 2 to the n. Here we have the resolution of identity. So, we use that, and then we are trying to develop integration with respect to resolution of identity, and that is why we are looking at this sum. So, what are these? These are E j by 2 to the n are projections. So, these are bounded operators, and G j by 2 to the n is a scalar. I am multiplying with a bounded operator and summing up, finite sum, right. So, these are actually bounded operators on the Hilbert space H, right, fine. So, claim is that then, so proof of this will take some time, not too difficult, but a bit technical. Then phi and g, so g is fixed, g is a continuous function. For each n I am defining these operators, right. So, I have a sequence of operators now on B of H. So, phi and g converges in the operator norm to a bounded operator. Of course, phi and g's are bounded operators. So, if phi and g converges to something in the operator norm, it is going to be a bounded operator, right. So, to a bounded operator. So, we need some notation for that, denoted by phi of g. So, there is no subscript n. Phi and g is like the nth Riemann sum of g with respect to the resolution of identity, right. That is what we are doing, phi and g, and claim is that phi and g converges to phi g, which is the notation phi of g, which is a bounded operator in the operator norm. Okay. And we have, so there are properties of the limiting. So, what should be phi of g? If you look at the definition of the integral with respect to some function f, right, the Riemann-Stieltjes integral with respect to, let us say, an increasing right continuous function f, you write it as integral g df, right. So, the phi g is going to be integral g d e sub t, right, with respect to the resolution of identity, and that is what. So, we are actually defining the integral with respect to a resolution of identity. Okay. So, we have the following properties. We have the following properties for the map g going to phi of g. Well, for any continuous function g in minus r to r, we are defining an operator, right. So, from c minus r to r, so that is continuous functions on minus r to r, to bounded operators on the Hilbert space, right. So, you can see the similarities between what we were doing, right. We had continuous functions on the spectrum, that was much more precise. Okay. Here the operator may have the spectrum minus r to r, but it may also be a very smaller set compared to minus r to r. Okay. That can happen. The ET may be a resolution of identity with respect to a self-adjoint operator whose spectrum is, let us say, contained in minus r to r. Okay. So, spectrum could be 0 to r, for example. Okay. But one still has a resolution of identity, and it makes sense for all t in R, right, except that it is 0 up to the left end point of the spectrum, and then it becomes 1 after the right end point of the spectrum, and so on, right. That is what happens. Okay. But when we write, we are writing it as supported in minus R to R. It may be supported on a smaller set. Okay. So, some of the things we have seen when we did things with the spectrum and the projection valued measure, some of the equalities may not be true. Okay. So, you may get an inequality and so on, but that should not bother us too much. So, we have the following properties for the map g going to phi of g. from continuous functions in minus r to r to bounded operators on H. So, what are the properties? Let us say one, g going to phi of g is linear, okay. That is a trivial thing always, because phi and g's are well most of the. So, we are going to prove these properties for the map g going to phi g by proving the same properties for phi n. So, if phi n has those properties, then because we are taking the limits, and if those properties are preserved under taking limits with respect to the operator norm, then the limiting function, that is g going to phi g, or the limiting map g going to phi g, will also have the same properties, right. That is all we are doing. So, g going to phi g is linear, phi of g star. So, that is the adjoint of the operator phi g, right. So, that is well phi of g star should be the complex conjugate of g, right, g bar. And well 3 with respect to the norm. So, I look at the norm of phi g is an operator, right. So, this is the operator norm, okay. So, let us write down that operator norm is less than or equal to L infinity norm of g, right, the supremum norm of g, okay. So, this is what I meant by you may have an inequality instead of equality. In the continuous functional calculus, we had an isometric isomorphism, right. So, there was a equality of the norm, but that was because it was between continuous functions on the spectrum and its image, right. Here we are starting with the general resolution of identity supported in minus r to r. We are not saying the support is exactly equal to minus r to r, support can be maybe 0 to r and so on, okay. But the theorem is stated in a slightly general fashion. So, that is why you have an inequality there, and for whatever one would guess, this should be an algebra homomorphism, right. So, phi of g h is equal to phi of g times phi of h for every g and h in continuous functions on minus r to r, okay. So, let me repeat, I start with a resolution of identity supported in minus r to r. I form these Riemann sums, okay. So, this we can call Riemann sums with respect to the resolution of identity E sub t, right. Then just like you prove the existence of the Riemann integral of a continuous function or Riemann-Stieltjes integral for an appropriate function capital F and g continuous, these phi n g's converge in the operator norm to some operator phi of g, which has these 4 properties, okay. Okay. So, I will I will ask you to check. So, maybe a simple exercise is exercise. So, remember the L2 of AB and E sub t we defined earlier, okay. What do you get if you do this procedure for continuous functions on AB, okay. So, what is phi of g for g in continuous functions on AB here. So, instead of minus r, so okay, so maybe I should write minus r to r, because we did things for minus r to r, right. It can be done for any interval, because we are developing Riemann degradation, right. So, with respect to resolution of identity. So, here let us write minus r to r just to be consistent with whatever we have been writing. Okay. Find out what we will get. So, remember the E t was defined to be multiplication by, so maybe I can write down that as well. So, E t is, okay, if t is greater than minus r, it is multiplication by indicator of, so let me write it as E t f, right. So, E t of f is indicator minus r to t f for t greater than or equal to minus r, okay. Identity if t is greater than or equal to r, 0 if t is less than minus r, right. That is how this was defined. Okay. So, you can try to compute this. So, you will get an appropriate Riemann sum and all that, and you will see what it converges to. Okay. So, that will give you an idea about why or what is happening and how you have an operator and you have a resolution of identity coming from the projection valued measure associated with that operator. Okay. Okay. Let us stop here. The next 1 or 2 lectures would be devoted to the proof of this and proving these properties of phi of g, which we will denote by integral of g against the resolution of identity E t. Okay. So, that is going to be the notation. Okay. So, we will stop here.